Hello and welcome to the first lecture of part 4. We're going to be talking a little bit more about categorical data. And before we get started, let me just please acknowledge SAS Canada for sharing with me all of the sample code that I have made available to you on my website, as well as some and many of the slides used in this presentation, as well as a few others, have come from some of their tutorials, which they've granted me permission to use in my lectures. So you have a categorical variable as an outcome. What do you do? So as we've seen in the previous lectures, distributions of variables are important to understand in order for you to be able to perform the correct analysis. So by examining the distributions of your categorical variables, you will be able to first of all, determine the frequencies of data values, which is always important for your descriptive statistics, and also to look for possible associations among the variables. So what do we mean by associations between categorical variables? So an association between two categorical variables will exist if the distribution of one variable changes when the level or value of the other variable changes. Now, if there is no association, the distribution of the first variable is the same regardless of the level of the other variable. All right, let's have a look at a simple example. So if you have a contingency table that looks like this, where on the top for your columns, you have happy dog and angry bull. And on your left, your rows are sunny weather and cloudy, stormy weather. So the question is your manager's mood associated with the weather? So if you look at the numbers, when it's sunny, you have 72% of the time your manager is a happy dog, and 28% of the time your manager is an angry bull. But when you look at stormy, thundery, rainy weather, your manager is a happy dog 72% of the time again, and 28% of the time is an angry bull. So would you hypothesize that there is an association with weather for your manager's mood? Looking at this, it is obvious that there is no association. Now let's look at this example again, but this time the numbers have changed. So during sunny weather, your manager is a happy dog 82% of the time, and only 18% of the time is an angry bull. Whereas when it's rainy and stormy, your manager's only a happy dog 60% of the time, and 40% of the time is an angry bull. So in this case, we can see from the numbers, and we don't really even need to do the stats to test it, that there is clearly an association. Let's talk a little bit about how to organize your data in a meaningful way. So categorical variables often are displayed in what's called frequency tables, which is basically a table that shows the number of observations that occur in certain categories or intervals. Now, a one-way frequency table examines one variable at a time. And if you see here in this table, let me just grab my pointer, we have our categorical variable, which is income, and it's made up of 3 levels: high, low, and medium. And these here are your, if you wish, your attributes or your descriptors. So for frequency, so you have frequency, you have your percentage, you have your cumulative frequency, and your cumulative percentage. Now, building on the frequency table, we now can see here that we have what looks very similar, but it is actually a cross-tabulation table. And basically, it shows the number of observations for each combination of row and column variables. And as you can see, we're just simply building towards what we are going to need in order to perform an analysis with categorical data. Now, you guys already know that when you're dealing with categorical data and you're working with SAS software, that you use the FREQ procedure for frequency, and you are well accustomed with the general form of the FREQ procedure down here. So I'm just going to zip along. Okay, let's jump into an example. So on the 10th of April 1912, the RMS Titanic set out on its maiden voyage across the Atlantic Ocean carrying 2,223 passengers. On the 14th of April, it hit an iceberg and sank. Now there were 1,517 fatalities. Now identifying information was not available for all passengers. So the question is, which of the following would likely not be considered categorical in the data? Gender, fare, survival, age, or class? So just think of an answer, put it in your head, and let's see what the answer is. So of course, I'm sure you all got the right answer, that fare and age are most probably continuous variables, so not considered categorical. Now, of course, you're thinking, well, we could categorize the data. Certainly we could. But, in this case, what was assumed is that fare and age would be continuous. Okay, what are our objectives? We're going to perform a chi-square test for association, which we've seen in previous lectures already, examine the strength of the association, and calculate exact p-values. Here's a useful table that I'm going to come back to many times throughout this course because it's a nice overview of what we cover in this course. And so as columns, we have the type of predictors or explanatory variables or independent variables, however you wish to call them. And this, we have categorical data, we have continuous data, and we can have continuous and categorical predictors together. As rows, we have the type of response, which is also the outcome or the dependent variable. We can have a continuous dependent variable, or we can have a categorical dependent variable. As we are talking about categorical data today, this is the reason that it's highlighted in red here, both categorical response and a categorical predictor. And what are we going to look at? What's called contingency table analysis. Let's get back to our example of the Titanic. Let's say we were interested in looking at a possible relationship or association between gender and survival, which are both categorical variables. We could put together this contingency table, and as rows we would have gender levels, which would be male and female, and as columns we would have survival levels, which is died or survived. In this case, we've chosen to give it a percentage for our frequencies, and as you can see, for females, about 30% of them died, whereas in males, about 80% of them died, which is right away is an obvious big difference. So the question is there an association? So the null hypothesis is, of course, that there's no association between gender and survival. The probability of surviving the Titanic crash was the same whether you were male or female. The alternative hypothesis is that there is an association between gender and survival, and that the probability of surviving the Titanic crash was not the same between the males and the females. So how would you test to see whether or not this association was not due to chance alone? And so we perform a chi-square test, which we've already mentioned in the previous lectures. And so when you perform a chi-square test, no association would mean that the observed frequencies equals the expected frequencies. Whereas an association, very simply, that the observed frequencies does not equal the expected frequencies. Now, just as you know, you don't have to do any calculations by hand, but just to know, the expected frequencies are simply calculated by the formula, the row total times the column total for that cell, divided by the sample size. Okay, so here is the equation for the chi-square test. And chi-square tests inevitably have corresponding p-values, which you need. And what they do is they determine whether an association exists, but they do not measure the strength of an association, and they depend heavily and reflect the sample size. So if you look down here, let me just grab my pointer quickly. If you look down here, this is your chi-square. It is the sum, okay, for each row and column of the observed minus the expected for that cell squared divided by the expected. Okay, so we've performed the chi-square test. We get a p-value. Now we are wondering, okay, what's the measure of the association, the strength of the association? So you'll see in your output that you'll have something called Kramer's V and phi listed. Now, both of these, Kramer's V and phi, are essentially correlations between categorical variable, which is what we're interested in. Now, because it's a correlation, as we've seen in the last lectures, they vary between -1 and 1, and in this case, anything over 0.25 would be considered, an association, something worth noting. Now, interestingly, the Kramer's V is always non-negative for tables larger than 2 by 2. In your case, most often, you're going to be working with a 2 by 2 table. And in this case, you use the phi correlation. And the phi correlation can vary between -1 and 1. So I'm sure most of you are thinking, I don't remember seeing Kramer's V or phi being reported in papers that I've read. And you're probably right. It's not often reported. It is not a common measure of association that people use. And the reason for that is, in medical research anyway, I think we tend to use the odds ratio, and there's reasons for that, and one of the biggest reasons is because it is the odds ratio that you report from a logistic regression, which we will go over in future lectures. So the odds ratio indicates how much more likely, with respect to odds, a certain event occurs in one group relative to its occurrence in another group. So in our example, how do the odds of males surviving compare to those of females? Well, the calculation of the odds is simply the probability of the event divided by the probability of a non-event, or 1 minus the probability of the event. Let's have a look at the differences between probability and odds of an outcome. So in the case of probability, it is simply the proportion of positive outcomes over the total number of outcomes. So for example, the probability of yes in group B here would be the total number of positive outcomes. So yes, there's 90 over the total number of possible outcomes for group B, which is 100. So then the probability of yes in group B is 0.9. So this is quite straightforward. Now, when we look at the odds, you'll remember that the odds is the probability of an event divided by the probability of a non-event. And so in this case, as we just calculated in the previous slide, the probability of an event is 0.9 for group B, which is 90 divided by 100. The probability of a non-event for group B is 10 divided by 100, which is 0.1. So the odds of a yes in group B is 0.9 over 0.1, which is equal to 9. So why is this useful to calculate the odds? Well, historically, it's from betting, and it's the way that you can calculate how much you're going to win when you bet. And so what bookies would do is they would post the odds against, which is, in this case, when they calculate the odds, it's going to be 9 to 1 for a horse to win, let's say. And in that case, you would know that if you bet $1, you're going to win $9 in return, because there's the odds of the horse winning is 9 times against the 1, and that's what started the whole use of odds. But in statistics, you can imagine we're not interested in betting, but the odds have some very interesting characteristics that can be leveraged in more complicated statistical analyses that we'll see later on. Now, of course, when dealing with odds, just like when we deal with probabilities, most often we want to compare the odds between groups. And in this case, for instance, Group A and Group B, we've calculated the odds for Group B. As we said in the previous slide, it was 9. The odds were 9 to 1. Now, when we calculate them for Group A, and you can do the calculation, 60 over 80 divided by 20 over 80, it is going to be equal to 3. And so the odds ratio of A to B is 3 divided by 9, which is 0.33. So when considering the odds ratio of A to B, keep in mind these properties. So no association is going to be 1, and that makes sense because your numerator and your denominator are going to be the same. So that means there's no difference, no association. Now, if Group A is more likely, you're going to have an odds ratio that's going to be between 1 and infinity. Whereas if Group B is more likely, then you're going to have an odds ratio that is going to be between 0 and 1, and it's going to be asymptotic, meaning that it will never achieve 0. Now, you can imagine when you're reporting an odds ratio, most often an odds ratio is reported as a number greater than 1. And the reason for that is researchers very often will just switch the relationship that they're looking at of A to B or B to A in order to get that number. You certainly can report an odds ratio between 0 and 1, but if you do, remember, most readers will expect an odds ratio that's 0 to 1 to be expressed as a protective effect when dealing with the association of interest. Okay, quick quiz. What tends to happen when sample size decreases? The chi-square value increases, the p-value increases, Kramer's v, or phi, increases, the odds ratio increases, or the width of the confidence limit for the odds ratio increases. So think of that, and we'll look at the answers in the next slide. If you answered B and E, then congratulations, you got the right answer. When looking at the 5 possible answers, we can see that a decreasing sample size, we would not expect the chi-square value, Kramer's v, or the odds ratio to be all that affected because they measure the strength of the association or will be affected by the strength of the association. However, a decreasing sample size will affect the standard error. And as the sample size decreases, the standard error will increase, and this in turn will affect the width of the confidence limit and the p-value. And there's your answer. So you'll recall from the previous lectures that when testing a proportion, we had the option of using the exact binomial equation, or we could approximate it using the standard normal curve using what was called the asymptotic standard error. So what we want to cover now is when not to use the asymptotic chi-square as described previously. And the simple rule is that when more than 20% of cells, so in your contingency table, have expected counts of less than 5, then you should not use the asymptotic standard error to calculate your chi-square because it will lead to a bias. So when looking at an example of a chi-square, which in this case has 3 columns and 3 rows, when you look at the expected counts for these 4 cells that have been highlighted, you can see that all 4 cells are less than 5. And because in this case there are 9 cells, that's 4 out of 9 cells, which is greater than 20%. And in this case, then, we would want to use an exact chi-square. Most often you guys are going to be working with 2 by 2 tables, and that in this case it's much easier. If any one of the cells has an expected count of less than 5, then you should use an exact calculation. So what you should remember is if you are dealing with small sample size, you should be considering an exact p-value calculation for your chi-square. If you have a large sample size, then this is when an asymptotic p-value can be used. So what do I mean by an exact p-value for the Pearson chi-square? Well, if we have a sample observed table here on the left, where we have our observed counts by rows and columns, and our expected table here on the right, where we have our expected counts that we calculated using the margins, we can state that the p-value will give us the probability of a chi-square value being as extreme or more extreme than the one observed just by chance. So the question would be, could these counts, these observed counts, occur just by chance? So how do we calculate the exact p-value? If you look at our observed table here on the left and you look at our marginal totals, let's look at what other combinations we can have in the observed totals without changing the marginal totals. And so we have two possible tables. This table here, and when you calculate the chi-square, it is less than our observed table, but with a higher probability. So this is the most likely table given the marginal values. Now, if you look at possible table 3, here's another possible combination of totals in the observed section considering your marginal totals, and you have a higher chi-square with a lower probability. So the exact p-value is going to be the sum of the probabilities of all tables with chi-square values that are as great or greater than the one observed in our observed table. And so the chi-square is 2.1, and therefore in this case there's only one other table that is as great or greater than our chi-square in our observed table, and so the p-value is simply going to be the sum of these two p-values, which is going to be 0.429. All right, that's it for lecture 1 in part 4. Just as a reminder, just the previous slides, we did the hand calculation for the exact p-value of a chi-square. Please remember, you do not need to be able to do that on your own. You have software that's going to calculate that for you. The only reason I went through it was for those of you who wanted to understand how it was being performed, and hopefully this will also give you an appreciation of when you would decide to use an exact p-value, because you'll understand the effect of a smaller sample size on the calculation of the chi-square p-value.